This audio abstract was created and produced by Arcadis. All statements, opinions, interpretations, and conclusions expressed belong to the individual speakers and do not represent views or policies of the Groundwater Monitoring Remediation Journal, Wiley Publishing, Arcadis, or any other entities. Hello, this is Craig Devine, and today we'll be speaking about our new article titled New Developments and Opportunities in 1,4-dioxane Biological Treatment. I've asked my co-author, Caitlin Bell, to join me for this conversation. Caitlin, thank you for joining. Would you mind starting off by providing just a brief background on yourself, who you are, and your experience?
Sure, absolutely. Glad to be here. I've been with Arcadis since 2007. My focus has largely been on bioremediation of various compounds, most recently including emerging contaminants like 1,4-dioxane. I am also our team lead for 1,4-dioxane in North America, so head up the group of folks, some of which are our co-authors here on this paper, who are well-versed in various treatment and investigation techniques for 1,4-dioxane in environmental media. Great,
thank you. So 1,4-dioxane has been a contaminant of emerging concern for a number of years, and it remains kind of a tough nut. Would you mind sort of setting the stage and it kind of highlighting where we are in terms of treatment options, both ex situ and in situ options? What are some of the technologies out there that are promising and developed and established and more innovative?
Absolutely. So when it comes to 1,4-dioxane, we're largely talking about concern of having it in groundwater, particularly groundwater that is sources for drinking water. So when we're looking at water treatment of 1,4-dioxane, the gold standard for a while now has been advanced oxidation processes. So using things like ultraviolet light and ozone and peroxide to generate hydroxyl radicals and other oxidants that will destroy the 1,4-dioxane in water. However, this can be kind of a costly treatment option, and so we've been exploring other options for ex situ treatment, whether that be things like bioreactors or absorbent media or other options for topside treatment. I think where a lot of the innovation has come recently is in situ treatment of 1,4-dioxane in groundwater. Again, historically, injection of chemical oxidants has been the go-to for destruction of 1,4-dioxane in groundwater. But we're learning a lot more lately about bioremediation of 1,4-dioxane in the subsurface. And so that's a lot of what we focus on in this article. And we try to highlight a couple of the successful in situ bioremediation treatment options for 1,4-dioxane, things like utilizing propane biosparge systems to be able to destroy that 1,4-dioxane more naturally and without the need for chemical oxidants.
You know, we've suspected and had evidence that biodegradation was an important mechanism for 1,4-dioxane for more than a decade, but it seems in recent years our understanding has really evolved. Would you mind highlighting our current understanding to date and summarizing some of the key features of biodegradation of 1,4-dioxane?
When it comes to 1,4-dioxane biodegradation, there's two primary mechanisms. One can be metabolic biodegradation, and then we're also talking about co-metabolic biodegradation. So normally when we talk about biodegradation, say for petroleum hydrocarbons, for example, we're thinking about metabolic biodegradation, where the microorganisms are gaining energy from that interaction to grow and produce more biomass. Conversely, co-metabolic biodegradation is a situation where the microorganisms are actually using a separate substrate for growth, so something like propane, for example, and the monooxygenases that are generated as part of that can also go on to destroy the 1,4-dioxane. So it's more of a fortuitous side reaction than the actual primary purpose of the microorganism. Now, both of these, both co-metabolic and metabolic biodegradation of 1,4-dioxane, is largely known to be an aerobic process. So either way, there needs to be some oxygen present so that the enzymes that are degrading the 1,4-dioxane from those microorganisms have the oxygen that they need in order to complete that reaction and to completely degrade the 1,4-dioxane to innocuous end products.
So you noted that there have been developments, particularly in the context of in situ applications for biodegradation of 1,4-dioxane. Would you mind describing what a system like that might look like and where we are in the life cycle of the technology?
A couple of projects that we've been working on over the last few years, we've focused on injection of gaseous substrates, so both propane and oxygen, into the subsurface in a biosparge type of system. So not a very aggressive bubbling, if you will, but enough so that there's a stream of oxygen and propane present, and those microorganisms can co-metabolically degrade the 1,4-dioxane like I was talking about before. In those situations, we've also found it helpful to add nutrients into the subsurface and sometimes also a bioaugmentation culture if we needed to have those specific microorganisms present that weren't there naturally. Now, some other folks are taking kind of a different approach to in situ bioremediation. So instead of injecting the gas, one can also extract the groundwater, inject the oxygen and propane or nutrients or bioaugmentation culture above ground, and then re-inject that treated groundwater into the subsurface to make a subsurface treatment cell where you're able to have all of the right things in the right place so that, again, that co-metabolic biodegradation can occur. So those are kind of two different ways that folks in the industry are approaching this sort of in situ treatment.
From an operational standpoint, what are some of the data types that you look at, and what are some of the system parameters that mark an optimally performing system?
Generally, our biggest metrics that we're looking at include things like dissolved oxygen in the groundwater. So that helps us understand the distribution of those gases, both the oxygen and propane from that example I gave earlier. We can use that dissolved oxygen to identify where we're getting that gas distribution in the subsurface and help make sure that there's enough oxygen present for that biodegradation to continue. So various studies have looked at what is the minimal threshold needed for oxygen to be present for this to be successful. We've found that operationally, we want to try to get to something like 4 to 8 milligram per liter of dissolved oxygen in that groundwater. The other thing we're keeping an eye on primarily is just 1,4-dioxane loss within the groundwater. So unfortunately, unlike chlorinated solvents, so your trichloroethene, we don't have intermediates to look at. So we're not seeing things like cis 1,2-dichloroethene or vinyl chloride generation to know that the biodegradation is occurring. We're only able to see the loss of 1,4-dioxane to help measure progress and success with this method. Now, we've done enough research and pilot testing to demonstrate that the biodegradation mechanism is occurring and is the reason for that 1,4-dioxane loss. So we feel confident in tracking those decreases in 1,4-dioxane as a measure of success for bioremediation.
So let's move on to ex situ applications for biologically based treatment of 1,4-dioxane. What are some of the developments in this area?
So largely when we're talking about ex situ bioremediation of 1,4-dioxane, we're talking about bioreactors. Now, what folks have been playing around with over the years are different types of bioreactors, and then whether to utilize a metabolic or a co-metabolic bioreactor. So I think the longest running bioreactor to date is a moving bed biofilm reactor at the Lowry landfill in Colorado that's been operating for nearly a decade now. They happen to have tetrahydrofuran in their treatment water, which acts similar to that propane I was talking about earlier and helps facilitate co-metabolic biodegradation of 1,4-dioxane. So more recently, folks have been looking at things like fluidized bed reactors, membrane biofilm reactors, oxygen-fed reactors, propane-fed reactors, combined reactors that treat chlorinated solvents first and then treat the 1,4-dioxane based on some ethane that was generated as part of that. So there's definitely some mixing and matching going on as we and as the industry are trying to find the right combination of things to quickly, reliably, cost effectively and sustainably operate these bioreactors and provide alternatives to things like those advanced oxidation processes I was talking about before.
That's very exciting. So, Caitlin, the age of biological treatment of 1,4-dioxane is finally here. What do you see as near and mid-range development trajectory for this technology?
Yeah, in the short term, we're looking at making pilot testing of in situ bioremediation more accessible. So we're putting together a mobile pilot test system that can be used at projects across the US to help lower that barrier to entry for remediation sites to evaluate bioremediation of 1,4-dioxane as an option. We're also teamed up with the folks at the New Jersey Institute of Technology to take a deeper look at the enzymes that are responsible for the biodegradation of 1,4-dioxane and try to help expand the understanding of that within the industry and help develop more effective genetic targets that can be used on projects more regularly to help track those sorts of things, like we were talking about earlier, to be that option to help verify that biodegradation is occurring and to help ensure that it goes successfully over the course of a project. Now, in the longer term, I think folks are also trying to help solve that challenge that I mentioned around things like compound-specific isotope analysis and try to help that be a better tool in the toolbox for evaluation of bioremediation of 1,4-dioxane. I'd say lastly, the other thing we're starting to try to wrap our head around is where else could we start seeing 1,4-dioxane in the environment? Folks generally think of it as a stabilizer for chlorinated solvents, but it can be present from several other manufacturing processes, as well as potentially present in firefighting foams. So we're actually starting to understand or try to understand whether 1,4-dioxane may also end up co-located with things like PFAS or other contaminants in the groundwater and in the environment.
Caitlin, this has been a great conversation, and thank you for your contributions to this article.
Thank you so much for having me.